In this video, we are going to talk about some of the application of electrolysis, as well as Faraday's law. And how do we use current and time of electrolysis to predict the amount of substances that can be formed. So first, let's look at one application of electrolysis. And this one is rather popular in the exam. So usually they will, maybe in the multiple choice or in the short answer question, this question will come up. So the production of chlorine gas, hydrogen gas, and sodium hydroxide. So these three chemical substances are actually all very, very useful in industrial applications. So a very nice thing is they can be produced simultaneously by electrolysis of concentrated sodium chloride, which is called brine. So whenever you see the term concentrated, you should be immediately know that the concentration is much greater than 1 molar. And as we discussed in the previous video, what this implies is that the order of the electrochemical series would actually change. If the concentration of the chloride ion is high enough, it can actually switch order with water and will be preferentially oxidized. So this is why we use concentrated sodium chloride. And now let's look at some of the possible reactions that can happen. So you have the sodium ion, you have the chloride ion. Because you have concentrated sodium chloride, you still have water because you are not dealing with a molten sodium chloride. So the setup is actually a little bit different. So it looks like this. So this is a membrane, and the function of that, we will discuss this a little bit later. And as before, you have two electrodes, and the electrodes are inert. And you have two different solutions. So let's make this side cathode and this side anode. We know that cathode undergoes reduction. So electrons are forced into cathode since we are talking about electrolysis. So the polarity is negative, and this is connected to the negative terminal of the power supply. Then we also have positive terminal, which extracts electrons from anode and forcing it to undergo oxidation. So the polarity is positive. So we actually have two different solutions in these two systems. At anode, we have concentrated sodium chloride. In commercial application, we have dilute sodium hydroxide as the electrolyte. And the membrane only allows sodium ion to pass through. So the hydroxide ion and the chloride ion cannot pass through the membrane. And let's look at the reaction that could happen in this system. So for the anode, we have water and chloride ion that can possibly undergo oxidation. because sodium ion cannot undergo oxidation anymore. It's already in oxidized form. And because from the electrochemical series, we know that if we have concentrated NaCl, then they are actually going to swap order. So instead of water being oxidized, the chloride ion will be oxidized preferentially, since we are not doing this electrolysis under standard condition. So it would actually look like this. And the state is still aqueous because we're not dealing with molten solution. Have chlorine gas plus 2 electrons. And the chlorine gas will be collected and stored for later use. So we have already produced chlorine gas. And also, from the cathode reaction, some of the possible reactions could be sodium being reduced or water being reduced. So let's have a look of which reaction would occur. So sodium ion is towards the very bottom, and water is above sodium ion. So we know that water will be reduced preferentially. So the reaction would be the production of hydrogen gas and hydroxide ion. Let's copy down the electrons flow as well. So this is the reduction half equation. And then we have another problem. We know that we got accumulation of the hydroxide ion at the cathode, so the charge is not balanced. So that's when membrane cell becomes important. It allows the positive sodium ion to go towards the cathode, and in that way, the charge is balanced. So you get extra sodium ion from the anode. And you also produce the hydroxide ion. And in this way, the concentration of sodium hydroxide in the cathode side will increase. And gradually you get a very concentrated solution of sodium hydroxide, which is what you want because you also want sodium hydroxide as one of your products. And that's why we separate, or we use different electrolyte for cathode and anode to ensure that we don't mix sodium hydroxide with sodium chloride, which would be very difficult to separate out. And that's why this whole process, or this whole apparatus is called membrane cell. So this is one of the applications of electrolysis. As you can see, if we use it correctly, we can produce a lot of useful chemicals. So the next problem you might ask, naturally, is how much of this product can I produce? So if I do an electrolysis under 100 amps for one day, how many chlorine gas and sodium hydroxide and hydrogen gas can I produce? And this is very well predicted by something called Faraday's law. So Faraday's law basically quantifies how much charge 1 mole of electron can carry. And it establishes this link between charge and mole of electrons. So this is really useful because charge can be linked to the amps and time of electrolysis. So it can be linked to how much electrical energy you have put in to your system. And number of moles of electrons are also important because from the mole ratio, we can easily predict how many moles of electron we require to produce a certain amount of chemicals. So essentially establishes a link between the amount of chemicals you can produce with the amount of electrical energy you have put in. So that's why Faraday's law is very useful and very important. So 1 Faraday is called 1F and is equal to 96,500 coulombs of charge. This is also in your data book. So the charge of 1 electron is 1.6 times 10 to the negative 19 coulombs. And we know that 1 mole of any substance is 6.02 times 10 to the power of 23. All those values are in your data book. And if you multiply these two numbers together, you get 96,500. So that's where this number comes from. So essentially it asks the question, how much electrical energy can be supplied by 1 mole of electron? And the answer is 96,500 coulombs of charge. And the unit is, it's very difficult to write this number every time, so we can also write 1 Faraday, which is much easier to write out. So I have mentioned coulombs of charge many times. So maybe let's have a look at what this actually is composed of. So coulombs is a unit of quantity of charge. So the quantity of charge has the unit C. So the quantity of charge is equal to the amp or amperage times time, which is measured in seconds. So Q equals to IT. So this tells you the amount of current you have times the time of your electrolysis is equal to the total amount of charge supplied. And this also makes sense because I is basically the amount of current or the amount of charge that pass through your system per second, and T is how many seconds you have. And when you multiply these two quantities together, you get the total amount of charge passed through in your system. So we can rearrange the formula a little bit. So we know that the mole of electron is equal to the quantity of charge divided by Faraday. So why is this the case? So the unit of Q is basically coulombs. So this is the quantity of charge passed through your system. And we know that 1F is equal to 96,500 C. And Q is also in terms of C. And this 96,500 C coincidentally is also the charge of 1 mole of electron. So if you have a ratio, so suppose that Q is equal to 96,500 C. Then you do 96,500 divided by 96,500. You get 1. So this tells you whenever you have 96,500 coulombs of charge, you know it is the equivalent as 1 mole of electron pass through your system. If you have more than that, you have more than 1 mole of electron. If you have less than that, you have less than 1 mole of electron pass through your system. So that's why I say Faraday is important, because it links the idea of charge with the idea of mole. So this is why it is important. It forms this connection between two seemingly unrelated subjects. So that's the two formulas that you need to know. Also, it's not formula, another rule which is very intuitive is as follows. The rule basically says everything should follow the mole ratio. So if you want to produce 1 mole of silver from silver ion, you need 1 mole of electron. If you want to produce 1 mole of aluminium metal from aluminium metal ion, you need 3 moles of electron. So you need to follow the coefficient basically. So this is Faraday's law. We will look at some application questions now. So now let's look at this question, and let's do this together. A solution of copper sulfate is electrolyzed for 30 minutes using a current of 0.500 amps. Calculate the mass of copper deposited at the electrode, and also the volume of oxygen gas evolved from the anode at standard laboratory condition. So first, let's look at the number of significant figures we need for this particular question. So here we have 3 significant figures. Here we also have 3. So we need to answer our questions in 3 significant figures. Okay, so what is the mass of copper deposited at the electrode? We first need to know that the reduction of copper ion requires 2 electrons. So the molar ratio is 1 to 2. And you can obtain this from the electrochemical series. So this is a very important piece of information. Then let's calculate the amount of charge. So Q is equal to I times T. And remember, T is in seconds. So let's do some conversion first. 30 minutes is equal to 30 times 60, which is 1,800 seconds. So Q is equal to 1800 times 0.5, which is 900 coulombs of charge. And now we need to convert these coulombs of charge to moles of electrons. We know that 1 mole of electron is 96,500 coulombs of charge. And now we have 900 coulombs of charge. So how many moles of electrons we have? We get 0.0093 mole of electron. And the next step is to calculate the moles of copper we can produce. We know that for 1 mole of electron, we can produce half a mole of copper because of this 1 to 2 ratio. So the mole of copper is 0.0093 divided by 2, which is 0.0047 mole. And the next step is to read the question again. We need the mass of copper. So the mass of copper is just the number of moles of copper we produced multiplied by the molar mass of copper, which you can obtain from the periodic table as 63.5 grams per mole. If you multiply this together, you should get 0.2976 grams, which is into 3 significant figures. So this is the mass of copper deposited at the electrode. The next question is the volume of oxygen gas evolved from anode. So now let's go to the electrochemical series to see which reaction is actually taking place. So you have the copper 2 plus ion, and you also look at the strongest reducing agent in your system. Look from top to bottom, and you get water. So this is the reaction occurring. So the reaction we have is 2H2O. So when we look at the molar ratio, it has a 1:4 ratio. For every 1 mole of oxygen gas evolved, we need 4 moles of electrons. So the mole of oxygen gas is equal to the mole of electrons, which we already know is 0.0093, divided by 4, which is 0.023 mole. And the volume of oxygen is 0.0023 times not the molar mass, but the volume of gas under SLC, which you can obtain from your data book as 24.8 liters per mole. And we have 0.0023 moles. So when you multiply these two numbers together, you get 0.058 liters. And this is exactly what the question is asking. It's asking the volume of oxygen gas evolved. Let's move on to the next question. Calculate the mass of iron produced when we electrolyze this solution for 1.2 hours using 0.75 amps. So now let's look at the first step is always to establish the chemical reaction you are doing. So you are doing this reduction equation. So we know that the nitrate ion has a -1 charge, and we have 2 nitrate ions. So the Fe ion must have a 2 plus charge. To turn this into iron, we need 2 electrons. And now let's calculate the moles of electrons we have by first calculating the quantity of charge. 1 hour 20 minutes, so 1.2 hours is 80 minutes. 80 minutes is 80 times 60 seconds, so 4,800 seconds. So this is the number of seconds we have, times by the amps, which is 0.75. You get 3,600 coulombs. We know that 1 electron or 1 mole of electron have 96,500 coulombs of charge, and we now only get 3,600 coulombs. So in fact, we only have 0.037 mole of electrons. We know that the ratio between electron and Fe2 plus ion is 1 to 2. So for every 1 mole of ion produced, we need 2 moles of electron. So a way you can think about this is because we need more electrons. So for a given amount of electron, we can produce less ion metal. So instead of multiplying by 2, you should somehow make the number smaller. So the only way you can make it smaller is by dividing by 2. (0.019 mole). And then the question is asking the mass. So the mass is just the number of moles times the molar mass, which is 55.8, 1.04 grams. Next question, what is the mass of the following metal that can be produced in a 2-hour electrolysis with 1.2 amps? So whenever you see a question like this, you should always be skeptical. Can you actually produce this metal based on what you see from the electrochemical series? When we go back to our electrochemical series, you should know that water is a stronger oxidizing agent than sodium ion. So whenever you have aqueous solution present in your system, you should never be able to produce any sodium metal. So you don't actually need to do any calculation with this question. And the answer is 0. You cannot produce any sodium metal from sodium ion. To produce sodium metal, you need molten sodium ion. So there's no water present, and then you can produce the metal. So a very tricky question indeed. So now let's look at number 4. So how long would it take to produce something with 80 amps? So now we are given the amount, the mass, which in turn means the number of moles of a certain chemical. We're also given the amps of current we have. The only unknown is time, and we are required to calculate the time. So first, let's convert 1 kilogram to 100 grams, because everything in chemistry we're dealing with grams. It is the standard unit. And then let's calculate the number of moles, which is 1000 divided by 58.7 from your periodic table. You get 17 moles. So how many moles of electrons you need? The reduction half equation looks like this. So for every 1 mole of nickel produced, you need 2 moles of electrons put in. So you want 17 moles of nickel. So you need 17 times 2 moles of electron, which is 34 moles. And how many charge would 34 moles of electrons give you? So 1 mole of electron, remember, gives you 96,500 coulombs of charge. So 34 moles gives you 34 times 96,500 coulombs of charge. Which is a lot of charge. And you already know you have a current of 80 amps. So Q is equal to IT, and T is equal to Q divided by I, which is equal to 328 1000 divided by 80. You get 4.1 times 10 to the power of 4 seconds. Next question, 2.5 grams of aluminium from aluminium ion. So the number of moles is 2.5 times divided by 27, 0.09 mole. If you look at the reduction half equation, you require 3 moles of electron to produce 1 mole. So in one sense, you can argue that aluminium is more expensive than electron. That's how I think about this. Although it's not entirely accurate, but because it's more expensive, you need more electrons to produce a certain number of aluminium. So the number of electrons you require is 3 times 0.09, which is 0.28 mole. And 0.28 mole times 96,500 gives you the charge carried by this amount of electron, which is around 27,000 coulombs. And time required is just this divided by 80. You get 335 seconds. 5.25 mole of silver. So they already given you the number of moles. So the reduction half equation looks like this. So it's 1-to-1 ratio. Thus we need 5.25 mole of electron as well. 5.25 mole times 96,500. You get this number, coulombs of charge, and then you divide by the current. You get 6.3 times 10 to the 3 seconds. So that's how you do questions related to Faraday's law. Really not too complicated. If you can get your head around about the charge that can be held by 1 mole of electrons, and also just looking at the mole ratio of your reduction half equation.